Welcome to the new unit for applications of integrals. The first thing we're going to look at is integrals as a net change. This is kind of like a physics application, but using calculus. We're going to compare between the distance versus displacement. So we have already seen how position of an object can be found by finding the integral of the velocity function. The change in position is a displacement. To see the difference between distance and displacements, we're going to do example 1. 2 steps forward and 1 step back. So it could look something like this. If we're talking about the total distance, that means that we had 1 step plus another step plus another step. So we traveled 3 steps here. Versus displacement, we only care about from where we started and from where we ended. So the only thing I'm going to look at for displacement is from my start to finish and that distance there, which is 1 step. So if we want to find the displacement or the change in position, we are going to integrate the rate of change over the interval. So mathematically, it looks like this. If we want to find the distance traveled, then we're going to integrate speed instead of the velocity over the interval. Recall that speed is the absolute value of velocity, so it just looks like your displacement one, but with absolute value around the v of t. Then finally, your new position is going to be your old position plus the change in position. Mathematically, this is s of b is equal to s of a plus the integral of a to b of v of t dt. So we're going to apply those 3 into an example. We've been given the velocity of a particle moving along the x-axis as v of t when the time is between 0 and 2. So if we want to know if the particle is moving left or right, or when it's stopped, we need to determine when is the velocity positive and when is the velocity negative. If the velocity is positive, then we're moving to the right. If the velocity is negative, then we're moving to the left. So we're looking for positive velocity here and negative velocity. And it's stopped when our velocity is 0. So I'm going to go ahead then and set this velocity equation equal to 0 so that I can solve for t. I'm going to divide both sides by 6. So when I do that, I get t squared minus 3t plus 2. Now I'm going to factor this, which is t minus 2, t minus 1. So that means our points of interest is 2 and 1. I'm going to draw a sign diagram so I know exactly what intervals that the velocity is positive or negative. So if I plug in, let's just say 0, we're going to get a positive number because that's going to be negative 2 times negative 1. If I plugged in 1.5 into our v of t, I'm going to get a negative. And if I plugged in, let's say, a 3 into our v of t, we're going to get 1 times 2, which is a positive number. So this means in this interval, I'm moving to the right, between 1 to 2, moving to the left, and then between 2 and on, I'm moving to the right. So we're moving to the left between 1 to 2, to the right between 0 to 1, and 2 and on. But again, if you look at our time, it's restricted to 2. So then I'm not going to say 2 of 2, I'm just going to leave it as 0 to 1. And then when are we stopped? We are stopped when our velocity is 0, and this occurs at 1 and 2. The next thing we do is find the displacement. So according to our chart, we find displacement by a to b of v of t dt. Our time interval in this case is from 0 to 2. And we know what v of t is 6 t squared minus 18t plus 12 dt. So I'm going to integrate each term by reversing our power rule, which is t to the power of 3. I would bring this 3 back down, but divide it by it. So that's 6 divided by 3 is 2, minus t squared, and then 18 divided by 2 is 9, plus 12t. And we're going to evaluate this from 0 to 2. So this is going to be 2 times 8 minus 9 times 4 plus 12 times 2. And then after we would subtract by 0, 0, and 0. So I'm just going to leave it like this and simplify it. So 16 minus 36 plus 24, which is 4 as our final answer for our displacement. If you want to find the total distance traveled, it says use a calculator. So we're just going to plug this into the calculator. It's going to be the absolute value of v of t. And we're just going to put that in the calculator and let the calculator do all the work here, which is going to be 6. Lastly, it says set up an integral, just to set up, so don't solve, to find the particle's total distance traveled without using absolute value. So this means we need to change the sign of any negative portions because absolute values will always be positive. So we're going to change sign of any negative portions, and that's because the absolute value must be positive. So if we think about our time interval to the right, which is positive already, that's going to be from 0 to 1, according to example 2a. It's going to be positive of v of t dt plus, and I know this value is going to be negative because according to my sign diagram in A, from 1 to 2, it's going to be negative. So then to counter that, I just need to multiply this entire integral by a negative so that it becomes positive. So here we're going to change the sign to make the value positive. And again, that's because we know that we're going to get a negative from our sign diagram in part A between 1 to 2. Let's look at another example. It says the tide removes sand from Sandy Point Beach at a rate modeled by R, and we also have a pumping station that adds sand to the beach at a rate by S. So both R and S have units of cubic yards per hour, and T is measured in hours from 0 to 6. At time 0, the beach contains 2,500 cubic yards of sand, and we're going to use calculator to help us do these questions. So if we want to know how much sand is going to be removed, we're going to look at R of T, because that's the equation for removing sand. And we want to know how much sand, we don't want the rate. So in order to get the amount for the sand, we're going to take the integral from 0 to 6, so we'll get a 6-hour period of R of T dt. Because R of T dt is the rate, but I just want to know the amount of sand. We can use our calculator for this, and this will give us 31.816 cubic yards. For part B, we want to write an expression for y of t. So y of t is the total number of cubic yards. Well, we know how much the beach has to begin with is 2,500. Then we want to find how much is being removed and also how much sand is being added. So in words, y of t is going to be the initial amount plus the amount added and subtract the amount removed. Algebraically, the initial amount is 2 2,500 according to the original part of the question, then the amount added is going to be from 0 to some time t of the amount added, which is s. And we're going to use another variable x because I can't use t again if I'm saying that t is our time. Then we need to subtract the amount removed, which is r. Being consistent, I'm going to use x of dx. So that is our expression for y of t. Now we want to find the rate at which the total amount of sand on the beach is changing at t equals 4. Okay, so we know the amount of cubic yards of sand from y of t and how that can be calculated. But in this case, if I took the derivative of this, I'm going to be left with the rate for that sand on the beach. So our next step would be to take the derivative of this, which is then going to be s of t minus r of t, using your fundamental theorem of calculus, part 2. Our next step is to evaluate this at 4. So looking at s of 4 minus r of 4, and you can just put that into the calculator to do that calculation, which is going to be about negative 1.909 cubic yards per hour. For part D, we want to find the amount of sand on the beach, and we want to find the minimum value between 0 to 6. We already have the equation y of t. This tells us the amount of cubic yards of sand. So what we can do is graph this y of t and try to find the minimum that way. And we can also evaluate certain points like times 0 and 6. At times 0 we know it's 2,500. At times 6 we can plug it in to y of t and find that's going to be 2,493.3. So then we want to find the minimum between there. So what you can do is put this into your graphing calculator and then press on the minimum part of it if you have a TI-84. If you want to do this on decimals, all you have to do is click on the minimum and you should get the time. It's going to be about 5.118 for the time of the amount of sand is going to be 2,492.4 cubic yards. So then your time is going to be about 5.118. Example 4, we're going to use a calculator again to assist us. We've been given the graph of V of t for Karen riding her bicycle along a straight road from home to school. And our time is from 0 to 12 minutes. So the first thing we want to do is find the acceleration of Karen's bicycle at time 7.5 minutes, which is located over here. We just need to find the slope of this, and that will give us our acceleration. So that's our change in y divided by our change in x, which is negative 0.1 over 1, which is negative 0.1 miles per minute squared. Remember that those are our units here. Now we want to explain the meaning of integral of 0 to 12, the absolute value of v of t dt in terms of Karen's trip, and then find it after. So if we look at the chart on the very first page, this describes the total distance. That Karen has traveled for the full duration of 12 minutes. So everything's going to be positive because of the absolute value. We're finding the area underneath the curve, and it's all going to be positive. So we're looking for this one here. So that means we need to find the area underneath the curve. So our first section over here is going to be 2 times 0.2, which is 0.4, divided by 2 is 0.2. This has the same area. Then we have 1 times 0.3 divided by 2 is 0.15. This is 1 times 0.3, which is 0.3. This little section here is 1 times 0.1 divided by 2, which is 0.05. Then this rectangle here is 1, 2, 3, 4 times 0.2, which is 0.8. And this little triangle in here is going to be 1 times 0.2 divided by 2, which is 0.1. So we're going to sum all of these up, and because it's the absolute value, we're just going to add all of them together. Which is 1.8 minutes. For C, we wanted to know when Karen leaves her textbook at home and then returns to get it. So this would be whenever our velocity is 0, because she would need to stop and change directions. Also, our directions when it's positive is usually going to a certain area versus going to the left or to the negative direction. So this occurs only one place, and that's going to be at t equals 2, because our velocity changes from positive to negative. So she's moving to the right, and all of a sudden she changed directions and moved to the left. Going to compare Larry and Karen to see how far away they live from the school. We're given Larry's velocity as w of t. So we can find out our displacement for Karen because we have all that information from our graph. So we can go ahead and do that. And then we can use our calculator to help us find the displacement for Larry. So your displacement for Karen is going to be integral from 0 to 12 of v of t dt. And we have all those areas already written in. We just need to now consider their directions. We have 0.2 minus 0.2 plus 0.15 plus 0.3 plus 0.05 plus 0.8 plus 0.1, which is 1.4. And then for Larry, that's from 0 to 12 of wt dt, and we can just calculate this in the calculator and plug it in, and we're going to get 1.6. So that means Karen lives closer because Karen is 1.4 miles away from the school. And then we're done.